All right, in this statistics section, we'll be talking about sampling distributions and estimators. Um, so we've got a lot of conceptually deep stuff in this section, and the work can be a little tedious. So I'm really important that you pay attention to the examples in this one. All right, so our general behaviors when we're taking sample size from populations, there's two properties that really apply. The first is that sample proportions tend to be normally distributed, and the mean of all of the sample proportions should be equal to the actual population proportion. So if you took a bunch of data and you just found different samples and looked at the proportions of those data, that if you took all the means of those, that it should be equal to what the actual proportion population is. So let me just give you, there's a nice visual that kind of works this through. So here's the procedure. We're going to sample, find a bunch of different proportions, and then so we find those proportions for each of our samples. And then if we look at all of those proportions together, they should be normally distributed. And we should be able to find their mean. And that mean should be the same as the proportion for the entire population if you took all those sample proportions together. So we're going to use that kind of process to do everything. And you can do this with means, so you can do the same thing. If you have means, you can take a bunch of samples, find the mean for just that sample, take all of those sample means, and when you put them together, you should have a normal distribution as well. Same thing with variance as well. This works with variance as well. If you take each sample, look at their variances for each sample, and you do those, your variances tend to have a skewed distribution, though they're not going to be normal because, remember, you're squaring the standard deviation. So when you square it, you're going to have some kind of skew. So that's our general behavior. We're not going to do a lot with variance, but we are going to do problems with proportions and with means. So very important that you'll see an example of those, see if we can walk you through it. So the sampling distribution of a statistic, such as a mean or proportion, is just a distribution of those values when we look at all the possible samples of the same size. So if we have a population and we want to take 10,000 samples and all those samples are each going to be we're going to take five data values. And if you look at those, whether it's the means of each sample, they should, again, when you look at all the means and you graph those means, they should be normally distributed. Same thing goes for proportion as well. Okay, so it's basically, this is the same slide. It's just changed from mean to proportion, but that's all pretty much the same. So a little bit of notation here. So X is going to be our number of successes. N is our sample size. Capital N is our population size. P hat, the little p with a little triangle-y thing on top of it, that's p hat. That is the sample proportion, which is X divided by N. And if you have a population, that's just P, and it's X over capital N because you're using population size rather than proportions. So important to know that means, X bars, and P hats are all statistics. They are not parameters. So P without a hat is a parameter. And the mu for the mean is a parameter because those deal with the populations. So we already talked about this, that the distribution of those sample proportions tends to be normal, and that the target, okay, the sample proportions target the value of that population proportion. So the more samples you have, the closer and closer that when you find the mean of the proportions from all your samples, you will be closer and closer and closer to the actual population proportion. So let's do some examples because, again, I think it's always easier when you see an example versus just talking about some, nebulous idea. All right, so we're going to just walk through this one together, and then we're going to do one by hand so you can kind of see. So consider repeating this process. You're going to roll a die 5 times, one singular die, and find the proportion of odd numbers. So your odds are 1, 3, or 5. And you want to know what the proportion is. So we roll the die 5 times. We do this over and over and over and over again. And we want to know the proportion of odds. Whoops, scrolled too fast. Okay, so what we're going to do is say the first sample, we only had 0.2 of those 5. So 20%. So 1 of the 5 times we rolled, we got an odd. Say the next time we did it, we got 0.4 probability. So two of the 5 times were odds. Okay, and you just keep doing this over and over. And when you start creating histograms of those proportions, so say you did this 10,000 times, you may get a histogram that looks like this. And notice how close to normal it is, right? It's tall in the top, goes down on each of the sides. So the more samples that you create, the closer and closer you'll get to that perfect, normal distribution. This also works for the means as well. Same kind of thing will happen when you create all those samples and look at the means over and over again. Then you put the means in a histogram, it will look like a normal distribution. So it's really kind of cool. So again, tends to be normally distributed, and it means that when you take those sample means, you're going to be targeting. The more of them you collect, you can start targeting the mean of the population if you don't know what it is. So we can use samples to, estimate to a very, very close, values what the population mean is. And we can do this with variance as well, but we're not going to do a lot with variance in this section, just to let you know. So couple of things. If you're trying to find the population standard deviation, this is and the population variance. Okay, so we talked about these in earlier sections. And variances, again, same thing works with variances. The more that you collect those variances from all your samples, make a histogram of all of those, it will start looking normally distributed so that your mean of your sample variances will be very close to the actual variance of your population. So it's really kind of cool how if you can get enough samples that you can actually get really close. Okay, so this example we're going to actually walk our way through. Okay, so we're back to rolling our die 5 times and finding the variance of the results. So again, you're going to roll the die 5 times, and for each of those samples, you're going to find the variance. So do sample 1, say you got a variance of 1.8. Sample 2, say you had a variance of 2.3, right? You just keep doing this over and over, and they say doing it 10,000 times. So when you do that, you get this kind of, notice it's a little skewed, which makes sense because it's a variance because it's squared, so it should be a little skewed. But notice that your peak is going to be over here, right? And so that's going to tell you that your variance is around 2.9, because I know that graph is little, but it's going to be around 2.9. And so when you find the mean of the variances, you should end up with 2.9 as your variance for the population, which is very close. So because the values that when you're rolling the die are all equally likely, so this one, go back. So I wanted to make sure that I tell you we do this 10,000 times. It's very important that we have lots and lots of trials. This will only work if you have lots and lots of trials. So they're all equally likely. 1, 2, 3, 4, 5, and 6. We're going to assume that the die is not loaded, or it's a trick die or something that's always going to roll a 3. But we should get a variance of 2.9. So that means that if we look at this, we could find the mean of these variances, and it should be very close to 2.9, which is the variance of the population. So we can always use our samples to help us figure that out. But because we don't often have population data, we have to use estimators, and that's what these statistics are for. That's what the samples are for. We're going to use them to infer or estimate the value of our actual population parameter, because sometimes it's very hard to find that. Now, there are some unbiased estimators in statistics, and we have a list of those. So here is our list. So our unbiased estimators are going to be proportions, means, and variances. Okay, these because they take into account every single data value. So they are unbiased because they're looking at every single data value. Now, we have other measures that are biased because they don't take into account everyone. So like median. Median doesn't take into account every single data value. Neither does range. And standard deviation can sometimes not target the value. So we have to be really careful with median, range, and standard deviation because they can have bias. But proportions, means, and variances do not. So these are the ones we really want to focus on. And that's what we will focus on in this section. So just so you know. And just an important note about standard deviation. It does not target the population because it has a bias if we have if the bias is relatively small in these large samples. So S is often used to estimate, our standard deviation of our population, even though it truly is a biased estimator. So I just kind of steer clear of S just because it can have bias, and I don't want to. Anytime it can have bias, I want to steer clear of it because that's gonna look not so well on my study. All right, so why sampling with replacement when we do these? Because every time we do, we want to put all the things back in the pot and pull a new sample. So you always want to make sure you're doing that. Because if you're taking a really small sample from a large population, honestly, it really won't matter if you're replacing or not. So you might as well replace, because then each of your events is independent and it gives you less issues to deal with down the road. And that's really wise. We want to make sure that we have those independent samples. Makes the math a little bit easier. Okay, so let's just walk through, and you're probably going, this all sounds great, but it doesn't make any sense to me. Okay, so let's talk about it. Okay, so let's assume that we have a population of 1, 3, and 8. And we are going to just put 3 ping pong balls, and we're going to grab 2 of them out, write it down, then we're going to come back in and do it again. And we're going to do this, a lot of times. This time they only want us to do it 9 different times. Okay, so they want us to find the value of the population standard deviation, okay, based on this. Okay, so step number 1, what do we do? Okay, if we're trying to find the standard deviation, okay, first thing we're going to need to know is the mean. That's kind of the biggest thing. So first of all, the mean, since it comes from our population, very easy. This is our population right here. Okay, these down here are our samples. So make sure you don't get the two confused. Notice they're trying to find sigma, which means the population. So first thing I need to do is find the mean. So I'm just going to add 1 plus 3 plus 8 and divide that by 3 because that is my entire population, which gives me a mean of 4. And then I can go and find the standard deviation, which is the square root of the sums of our x's minus the mu's, those being squared, and then divided by this. So because we have only 3 numbers, it's actually really easy to do this by hand. So my first one is a 1, subtract the 4, square that. And then we're going to add that to the next one, which is 3 minus the 4 and square that, plus the last one, which is the 8 minus the 4 and square that. So again, you can put that all in your calculator all at once. And then whatever that is, you're going to divide by 3. And then take the square root of it. So you can actually put this, you maybe do it in steps, do this one first, and then divide by 3, and then take the square root or whatever that is. But you should get 2.944. So again, be really comfortable with your calculators because that is going to help. All right, so this is our mean for our population. This is the standard deviation of our population. So far, so good, nothing major, nothing crazy. Okay. Part B of this question. All right, find the standard deviation for each of the 9 samples. And this is where it starts to get a little crazy, right? Because we've got 9 samples to do this for. So you'll have to go through and do this for every single one. And I know this is not fun, so I apologize in advance because it can be a little crazy. Okay, just had to get my notes there. Sorry for the pause. Okay, so for each sample, you're going to go through and you have to find the mean and the standard deviation for each sample. So what we just did on the last slide for the population, we're going to do for each one of these. And I'm just going to show you the first couple ones how to do it, and then I will tell you what the answers are to fill in these charts. Okay, so the first one, so say we got the 0.11. All right, what's the mean? What's the x bar, right? Well, 1 plus 1 divided by 2. 2 divided by 2 is 1. So there's our mean. And then your standard deviation. Oh, whoops, that shouldn't be a sigma. That should be an S because this is a sample. So let me erase that. Whoops. There we go. Okay, so I need my pen back. Why is my pen not working? Hold on. All right, finally got my pen working. Okay, so we're going to do the square root of take the first one minus our x bar and square it, plus the second one minus our x bar and square it, and then divide that by 2 because I had 2 samples in here. Oh, it should be n minus 1. Oh, 2 minus 1 in the denominator. Remember, when you're doing standard deviation for a sample, you always do n minus 1 in the denominator. Okay, so this is 0 plus 0. Well, it doesn't matter what the denominator is because 0 divided by anything is 0. So the square root of 0 is 0. So notice in my sample 1, 1, the standard deviation was 0. And you're just going to repeat this process with every single thing. So I'll do the next one with you too. So 1, 3, because that one's blank on the chart. Okay, so find your x bar. So that would be 1 plus 3 divided by 2. So 4 divided by 2 is 2. So that's my mean. And now let's find our standard deviation. So it'd be the first data point is 1, so 1 minus 2, square that, plus, next one is 3, 3 minus our x bar, and square that. And then divide that by 2 minus 1, 2 data points minus 1 because it's a sample. All right, that would give me, let's see, that's negative 1 squared, which is 1. And 1 plus this was squared is 1, that'd be 2, so 2 over 1, so the square root of 2. And the square root of 2, when I put that in my calculator, is 1.414. So I put that here. So you're going to go through and do that for every single sample. And yes, I know it's tedious, and I apologize. But you will need to do this for every single problem. So I'm just going to fill in the rest of this chart for you so that you can see what it looks like. Okay. So when I do 1.8, which is the next one, I get 4.95 as my sample. So if you want to pause this video and then try them yourself and see if you get the same ones, that would be great. And then you can unpause when you're ready. So 3.1, when I put that in there, we get exactly the same answer as when we did 1.3. I do 3.3, let's see, 3.3, I get 0 again. When I do 3.8, I get 3.536. When I do 8.1, I get 4.950. And when I do 8.3, I get 3.536. And when I do 8.8, I get 0. All right, so I've filled in my chart. Now I want to look at the probabilities. Now, the probability of each sample is the same. It's 1/9 because they're independent. We used replacement. We put them back in before we chose our next sample. So we can summarize because we notice there's some repeaters. Like if you notice that we have 9 results, right? Because we had 9 samples, and 1, 2, 3 of them, 3 out of the 9 were 0. So that's a probability of 1/3. So I have a 1/3 possibility that I'm going to get 0 as my standard deviation. The next value I saw was 1.414, and I had 2 of those. So 2 out of the 9 were that standard deviation. And then 3.53, I had 2 of those as well, so that was 2/9. And then 4.95, I had 2 of those as well. So this is my probability distribution of my standard deviations that I got from each of my samples. So yes, it's a lot of work, but it will pay off in the end, I promise. The good news is the math itself is not hard, it's just tedious. So just is very repetitive, and you're going to do the same thing over and over again. All right, so if I'm trying to find the mean of these probabilities, of these standard deviations, I need to use these probabilities because it's going to be weighted, right? Because some of them have happened more often than not. Just lost track of where I was. Hold on. That's part B. Yes. Okay, where's my part C of this problem? Okay, here we go. So part C. So now we're on to part C. Sorry, I had to double check. There's a lot of slides on here. Okay, so part C says find the mean of the sampling distribution. Okay, and I gave you a hint. It says the mean of the sample is the sum of the 9 total standards divided by the number of samples. Okay, and that can be a weighted mean. So from that last, we had 3 samples that had a probability of 0. Plus we had 2 that had a standard deviation of 4.14, or that had a standard deviation of 0, sorry. And then we had another 2 that had a standard deviation of 3.536. Plus we had another 2 that had a standard deviation of 4.950. And then we divide that by all 9 of our samples, right? We had 3, 4, 5, 6, 7, 8, 9, right? So weighted means, another place we can use weighted mean. So put that on my calculator. The numerator is 19.8. I'm going to divide that by 9, and that's going to give me 2.2. So that means my x bar of, and I'm going to put a little lowercase s there to tell you that that's the mean of my standard deviations for this problem. Okay, so we've calculated all the stuff. Now part D of this problem says, do the sample standard deviations target the value of the population standard deviation? And we already talked about this on an earlier slide, and you may be tempted to say yes, you may be tempted to say no, but we want to make sure that you're thinking this through. So the first thing you have to remember is that sample standard deviations are biased. So anything that says unbiased, we can get rid of because we know standard deviation. Variance is unbiased. So if this was variance, it'd be different, but it's not. So because we can get rid of this one, we can get rid of this one. So options B and C are out because standard deviation is a biased estimator. So we know it's either A or D. Okay, so let's read those two. Sample standard deviations do not target the standard deviation, therefore the sample standard deviations are biased estimators. Then part D and option D says the sample standard deviations do not target the population. Standard deviate, they say exactly the same thing. Oh, they do target and do not target. That's the only difference. Okay, and because we know they're estimators, we know that they do not target the population. If they did target, then they would be an unbiased estimator, but they don't. So D has to be the correct answer here because those standard deviations are biased. So we know it had to be either A or D, and then if they're biased, they do not target. So the correct answer is D. So again, you have to know not only the definitions, but you have to remember. But you can do this process for proportions, you can do it for means, you can do it for anything. We just happen to do it for standard deviation on this one. But you will see problems when you practice that do it for all different kinds, proportions, whatever. So just in general, remember that sample standard deviations, if they do target the population, then they would be unbiased. So if they say that specifically in the problem, then it's okay. But if they don't tell you, then just assume it's an unbiased, that it is a biased estimator and it will not target the population. Biased estimators usually underestimate or overestimate the parameter, which is why standard deviation can do that. It can over or under estimate, and we don't want that. Unbiased sample statistics, so proportions, means, those make good estimators. So you have variances, those make good estimators. So those are the three you really want to stick to and kind of avoid standard deviation because it can be a little bit off. All right, so go practice some of these problems. I'm sorry that they're tedious, but I have full faith that you can do this, and I will see you in the next lesson.